on from the. There you go. So it's my pleasure to introduce to you Ant. Ant has graduated with a PhD from University of Birmingham in UK. He worked actually on star data. Was it star? I think it was written, right? Cover. Now he's a long-time collaborator on ALICE with us, and he will actually become a deputy spokesperson on 1st of January. So thank you very much, Ant, for having time for us to discuss the very exciting new results from LHC. Take it away.
Okay, we'll get started. So thanks immensely for the invitation. I hope you enjoyed the talk. So the main purpose is to show you the first light ion results by ALICE, in particular in perhaps a theoretical context regarding what it could mean, and also in the context of what the other LHC experiments have seen. Okay, and I'll just run through the outline. I try to keep it somewhat simple and just ask some generic questions, such as what does a QGP look like in lead-lead collisions, and indeed did we find one in proton and proton-lead collisions. And this is something that we carefully addressed in our ALICE review paper that was published last year, which I was very happy to see. And also there were some key contributions from LB and L to this paper, in particular the jet section from Peter Jacobs and James Monaghan. And they did a very nice job there. And then, of course, what follows on from that is, number one, how did we perform in this light ion run? And perhaps a bit more centrally, have we found a QGP in oxygen-oxygen and neon-neon collisions? And what I show here is what the ALICE-3 detector looks like in run 3. It benefited from substantial upgrades. So now we can read out 100 times more heavy ion data than we could before, courtesy of the new TPC. And there's been a huge performance in the tracking too, courtesy of our new ITS, our silicon detectors, which again, Berkeley had a key contribution in making a reality. So the QGP itself, this is something that is predicted on a fundamental level, I would argue, in particular with the use of lattice QCD, which can calculate QCD in both the non-perturbative and the perturbative regimes. And what the calculations indicate at around a temperature of 155 MeV, the quarks and gluons are no longer confined. And this is associated with large pressures and large entropy densities becoming apparent when the temperature gets hotter and hotter and hotter. So this is really kind of one of the fundamental motivations for the field, essentially. The pressure is just denoted by the red bands and the entropy density by the blue bands. So as I wrote in my abstract, I think really a seminal moment in the field of heavy ion physics was the announcement of the perfect liquid at RHIC, and this was about 20 years ago. I just started my PhD in STAR. I had no idea what it meant at the time, but this statement was essentially based on a careful assessment of all the RHIC experiments, and they were produced 4 white papers. These turned out to be some of the most highly cited in all of experimental nuclear physics. And yes, at this point, I would argue it was a new beginning for relativistic heavy ion collisions. In particular, what state of matter are we actually forming, and how does it evolve? So then the question is, well, how do you establish such a claim? And there were kind of 2 key measurements that performed a lot in heavy ions, and of course we've performed them in oxygen neon collisions. And the first relates to the development of anisotropic flow. So if you start off with an initial state that's spatially anisotropic, then because of that, you have larger pressure gradients in these sort of exome X and Z directions compared to the Y direction. And this means that the momentum is anisotropic. And this is something we can measure and measure very well. One way to do it is just looking at two particle correlations versus the angular separation. And then what we extract from those is essentially Fourier coefficients. We refer to them as the anisotropic flow coefficients, and these corresponds to the amplitudes of the cosine distribution. V2 tends to be the largest, and it's a direct result of shapes such as this almond type shape. So it's something we can measure and measure very accurately. And this is one of the things I'm very proud of being an ALICE collaborator. Our measurements of V2 are very popular with theorists. In particular, I have a nice example here where this anisotropic expansion, number one, is well described by hydrodynamics for the hadrons that we produce. And to do so, these hydrodynamic models need as an input, number one, the QGP equation of state, something you can get from lattice, and number two, small but finite viscosities. And this was also quite a groundbreaking paper because it was one of the first times we used Bayesian analysis to essentially determine the posterior distributions of these QGB properties of interest, and that's represented by the by this band. And you can see that the viscosity over entropy density for the QGP is much lower than any form of matter, and actually quite close to a fundamental prediction from ADS CFT. The second sort of essential facet of our perfect liquid discovery, if you like, is the role of jets and their interactions with the QGP. And I think many of you know this, but one way to characterize the jet behavior, so to speak, is to measure this nuclear modification factor, which is just measuring a rate of high momentum probes appropriately scaled relative to PP. And this is a nice compilation that we had in the ALICE review paper where you can look at it for high PT charged particles or the jets themselves. There's a significant suppression in this across a wide PT range. And even though I don't show them, they're very much consistent with theory calculations, which assume that we have both a dense and deconfined system. So where it got quite interesting at the LHC, I would argue, were these sort of hunts for QGP behavior in proton-proton and proton-lead collisions, in particular, very, very high multiplicity. We were able to observe something that we refer to as strangeness enhancement. This is just the ratio of strange hadrons over non-strange hadrons. And what you can see is in proton-lead collisions, these increase quite rapidly when the event activity increases, and they approach values consistent with lead-lead collisions in the highest multiplicity proton-lead collisions. So that was indeed very interesting. We've also observed an isotropic flow. However, I would argue the consensus now that even though we're fairly sure this is a collective effect because we've measured it with multi-particle correlations and whatnot, the hydrodynamic description, in particular, this application where they try to use a common set of parameters to describe the flow in lead-lead and xenon-xenon, when you do so for proton-lead and proton-proton data, the agreement isn't perfect. And in fact, for the proton-proton collisions, the hydro calculations are about 30% less than what we see in the data. So we see flow, but I think the quality of the hydrodynamic description in the smaller systems, at least in my opinion, is not as competitive as the larger systems. And of course, we tried to search for jet quenching. So this is these RA measurements. We have central lead-lead here, peripheral lead-lead here, and proton lead right here. And within the uncertainties, we cannot claim a deviation from one. Many people have tried to put quite careful limits on this effect, and actually in the ALICE review paper, we were able to put an upper limit of jet quenching effects on the order of about half a GeV over C energy loss, and that is pretty much the best we can do in proton-lead collisions. So we see strangeness enhancement, we see a flow which we can't describe as well compared to lead-lead, and we struggle to see jet quenching. And this is really the motivation to run light ions, so to speak. So here we have a nice illustration that Atlas produced where you can just compare the system sizes in proton lead, in oxygen oxygen, and lead lead. And you can see it kind of sits in a gap, so to speak, between both the small collision systems and the large ones. And of course, before the data, there was quite a lot of activity, essentially making predictions to what flow might look like, as assuming that we have some hydrodynamic evolution that needs a QGP equation of state. I have one example here, and this is work from Nicholas Summerfield, who was an undergraduate at the University of Houston. We teamed together with some hydro experts at the University of Illinois, Urbana-Champaign, and a low-energy nuclear structure expert, Dean Lee, at Michigan State. And essentially, we employed some modern low-energy nuclear models for the shape of the nucleus, and then we evolved it hydrodynamically. And this is what we predicted at the time. Many more came since then. In particular, there were some predictions for neon. It kind of continued this thing where we start to try and use these sort of modern low energy structure modules, e.g. the GM or the NLEFT as an input. And here are the predictions for flow versus centrality. Neon is the red, and oxygen is the blue.
Ant, can I ask a question?
Yes.
So in this, thanks for reminding this PRC on oxygen. You have two types of calculation. One is Wood-Saxon and Wood-Saxon plus quarks. So if I recall correctly, that means that you localize valence quarks
that's a good question. Yeah. So the Wood-Saxon is not a modern input. It's just taking scattering parameters of the nucleus size and then put it in that distribution. So that's something we looked at. And then another configuration is we added substructure via the quarks to look at the effect on flow. And when we refer to alpha clustering, we actually use the NLEFT input. Now, alpha clustering actually emerges from this model. It's not put in by hand. So these models try to calculate all possible interactions and correlations, and then you get an output. And if you look at the output, you see many events, so to speak, where these alpha clusters pop up.
So, okay, I don't want to preempt the discussion, but can we have, do we have now experimental sensitivity?
I think so.
These curves are almost on top of each other. And then there's this crossover happening if you go along the centrality, right? Which is in V2 especially, right? The sort of Wood-Saxon and quarks gives you something smaller at very central events, and then something larger than just Wood-Saxon and higher centralities. Anyway, just I forgot about this calculation. I think it's interesting if we can measure those differences.
Well, the short answer is there is much more sensitivity, in my opinion, to be achieved when you divide the neon flow by the oxygen flow. And that's something that we'll see later in the Alice results.
Okay.
Did this sort of thing. So, as well as trying to establish QGP-like behavior, we also know flow is sort of sensitive to, the shape of the matter that's produced. And in particular, this is quite a surprise when we actually measured flow in xenon-xenon and divided it by the flow in lead-lead. It turns out to describe this ratio, you need to impose a deformation on the xenon nucleus. We know the lead is very spherical because it's double magic, but at the time, particularly this isotope, the 129, we had no information on the deformation. We had the neighboring isotope where there was a measured deformation, and then there was another neighboring isotope with a predicted one, so to speak. And essentially, the way this works is, if something's deformed, there might still be rotational timescales involved. So on average, the thing is spherical, but those timescales are actually much less than or much greater than the collision time itself. And that, in principle, provides us some sensitivity to the shapes of these nuclei. And this was performed for neon over oxygen calculations. So we've known neon is actually very deformed for quite some time from low energy. But if you then sort of use these modern nuclear structure calculations, the deformation essentially emerges from them. Oxygen itself is quite spherical. There might be some contributions from alpha clusterings. And this is essentially the prediction of the neon V2 over the oxygen V2 with these two different types of nuclear models. And what you see is, like in xenon-xenon, when you get to very central collisions, then the sensitivity to the shape becomes quite apparent. Now, I don't show it here, but these have also been performed, just assuming the neon has a spherical shape. And in that case, this ratio would be below 1. So if it's above 1, then that should be some indication that we might be sensitive to this geometrical structure of the neon 20 nucleus. Also, many jet quenching predictions. I mean, I show some from a few years ago that were put in the Alice performance paper, where we were essentially trying to figure out, well, what's the size of the effect and how accurate is our data going to be? And then many more sort of came about, certainly quite recently, where I have one from the hybrid model here, and then another one from the trajectum authors. They call it the simple model. I have no idea why they call it the simple model, but the paper is here to look at. You know, the nice things about some of these predictions is they really try to tune these models on heavy ion collisions, so to speak, and then ask, well, what's the corresponding suppression that we expect in oxygen or neon? And it turns out these suppression effects are up to 25% below unity. So that's what we're essentially trying to chase in the data. So let me go to the performance. So the LHC performed remarkably well and was able to deliver roughly 10 times what we had targeted in terms of the luminosities for all 3 collision systems. And I'm also happy to say that Alice was able to record most of that luminosity. So you have the performance of proton lead here, oxygen here. We don't have a similar plot for the neon, but what I do have is myself in the control room right before we were about to take the neon data and a recent postdoc Florian. So it was a lot of fun, but also quite worrying because you only have one shot at this. So you have to make sure all your detectors work. All these people actually really contributed nicely to the operation of the MCAL as well. And that performed absolutely magnificently. So we ended up getting about 1 inverse nanobarn of neon data, which corresponds to roughly 1 billion collisions. And we were 98% efficient. And the detector, I think, performed really well. So as soon as we took the data, there was quite a fast and high quality Alice data reconstruction. Typically, our reconstruction goes through a few calibration procedures, but when we did put in the calibration corrections, actually this really didn't change too much of how the data looked. So that really showed, I think, how well it worked. I have an example of the neutral kaon peak here. The middle is the pi0 peak reconstructed from 2 photons. And we have a beautiful heavy flavor D0 peak here, which is reconstructed from kaon and a pi. So all this was great. So we really had a huge incentive to try and make this data as public as quickly as we could, and also make sure it was high quality. So one thing we also looked at, and I write how clean are the beams here, but for several years, in particular, Spencer and John pointed out that some of the collision products have the same charge to mass ratio as the beam, which means in principle, you can have a hadronic collision or an electromagnetic collision. It can produce other nuclei that, because they have the same charge to mass ratio, in principle, they can stay in the beam. This is a nice little snippet on the CERN website. And I think actually what was nice about studying this is in the end, we had a close collaboration with our Alice alchemists. So a few of the people behind the lead to gold paper that got quite so successful, a lot of the physics is quite similar. And that collaboration was done with them, the LHC accelerator team, other people from different experiments, essentially to try and estimate and minimize what we refer to as transmutation, which is just the production of new nuclei that might stay in the beam. This is something that John studied extremely carefully, and I have some studies here that he presented in September. But what you can see are examples of the capture cross-section. So this is the cross-section for the produced transmutated nuclei to stay in the beam. And what you can see here is estimates of the integrated luminosity from different collision species divided by the integrated luminosity just from oxygen itself. So this was studied, theoretically it was modeled, but then as RHIC gave us a charge for, we of course had to look in the data to see if we could find any effects of transmutations. And one very simple thing you can do is this is just a multiplicity distribution or a model of a multiplicity distribution. And what one can do is slowly add helium-oxygen collisions to oxygen-oxygen collisions. And indeed, if we have a buildup of helium, this is going to collide with the oxygen at some point. These multiplicity distributions have many more events at low end charge. And you can see if you start adding the helium oxygen to the oxygen oxygen, you begin to see a slow increase in the amount of low end charge or multiplicity events. So we had a look in the data, and this is something that's very similar. So number of primary vertex contributions. Here we're just counting the number of charged particles at mid-rapidity that are associated with a vertex. This is actually quite a stable measure. It's quite time independent based on previous data, assuming things are working well. And what one can see here is just pretty much what you see on the left, but actually measured in the data on the right. And at 5 hours, we really didn't see any change in the multiplicity distribution compared to half an hour. So we haven't seen any evidence of transmutation in oxygen data. There were some limits that were established, and I think perhaps maybe we're consistent with upper limits of that, but we don't see the signal by itself. Things were a little different for neon-neon collisions. So here you see the same thing, the multiplicity distribution versus time. And for neon-neon collisions, we did actually begin to see an enhancement in the events with a small number of charged particles, so to speak. So just to give you a better idea, what you can do is you can take the ratio of neon late times divided by the initial time, and then at 5 hours, you sort of see this buildup of around 1% extra events. And then at 10 hours, this goes to around 2%. The black is oxygen. What I think is interesting about this is, number one, the luminosity was pretty much leveled for Alice, which means the amount of pileup doesn't change over time. We even added pilot rejection in here and took it out, and the effect stayed the same. So the luminosities were leveled, and also the oxygen luminosities. If we define it as the average number of collisions per bunch crossing, this was also the same in oxygen compared to neon. So we don't think it's due to pileup, but we're certainly not sure it's due to the transmutation either. This effect is much larger than the current estimates, and it's a little bit of a mystery. I have some backup slides that might help the discussion. what you see on the right is just the mean number of charged particles at later times divided by the early time. And this gives you some idea of how it affects things. And essentially, we see shifts of less than 1%. And most of this excess is at low multiplicity, peripheral collisions, which are not often analyzed. So even though we see something interesting going on, it's certainly perhaps large enough to be interesting, but it's certainly small enough to have a negligible effect on the physics analysis. So some of the analysis that we shared at initial stages, many people checked the stability versus time. Some saw a slight change, some didn't, but the systematic limitations tended to come from other sources. And this is something we'd like to understand and study further. So moving on to the physics results, so to speak. So this is what we showed at initial stages. This is just counting the number of charged particles in 0 to 100%. You can think of the charged particle yields, at least I like to think of it, as something related to entropy production in these collisions. And I think where it gets quite interesting is when you take these charged particle yields and you divide it by the number of participants, which we think is proportional to the volume. And this essentially should mimic an entropy density, so to speak, something that gets very much bigger as you form a QGP. And what you see is this much more rapid growth in the oxygen and neon compared to lead-lead at similar volumes. And the peak densities are also similar to what we see for central lead-lead collisions. So this is already an indication that something interesting might happen. It's certainly not a proof of QGP formation yet. Important for the initial condition. So we measured the anisotropic flow in oxygen and neon collisions. We submitted it for publication just before initial stages. Actually, Atlas managed to submit it one day before, so congratulations to them. But I'm hoping we'll be the first to publish. But I suppose that doesn't quite matter. The physics results really matter, and these are essentially just measurements of our V22, our V24, and our V3 in oxygen and neon collisions. And then, of course, the big question is, how well does Hydro describe this? I can absolutely state that these were really predictions, not postdictions. So these calculations that I showed before are actually described quite well, describe the Alice data quite well. Now, you can also think, well, which nuclear structure model does best? And in terms of the absolute values of the flow coefficients, maybe one can argue that NLFT does a little bit better than PGCM. So this is really quite fascinating. Now, there are other hydro implementations. Some of them describe the data equally as well, and some of them not quite as well. But I think when you just take the global picture, we've certainly achieved better descriptions in oxygen and neon compared to what we did for proton-proton and proton-led. Now moving on to these flow ratios. So this is the flow ratio in neon over oxygen. This is our beautiful data. Systematic uncertainties are actually very low on this measurement, around 1.5%, which is really what we need to discriminate between theory. And what I show is a trajectory calculation using the NLFT model. It predicts an enhancement like in the data, but it doesn't quite describe it quantitatively. The PGCM model does a little better. So these are crossed lines, and this is the data. And what we also did is look at different hydro calculations, usually the PGCM model, but in this case, the nucleon substructure characteristics were indeed different. So in the case of the models that describe the data best, the 3D Glauber and IP Glasmer, they needed a subnucleon width of around 0.1 Fermi over V. And by subnucleon width, what you do is you impose a structure for the nucleons, so you can see constituent quarks, but then the width is somewhat of a free parameter. In the trajectory model, I think they use 0.5 Fermi over C. So you can also arguably see a sensitivity to this. There are other measurements too, completely independent of this, and deep inelastic scattering, ultraperipheral collisions that can perhaps also be used as an independent cross-check for these types of features. So the story is pretty similar for CMS and LHCb. It's difficult to compare the data directly because there's different eta and PT cuts, and the flow depends both on PT and eta, but actually one does reach pretty much the same conclusions in terms of which models describe the data well and which don't. This is a really interesting measurement from LHCb. So this is not neon-neon, this is lead-neon. Divided over lead argon. And in that case, your deformed nucleus, or the structure of it, these are much larger imprint on the type of matter that you create. And because of that, you see even higher values of these ratio of sort of deformed over spherical. And this is what they see for V2, and this is what they see for V3. So overall, I think a very consistent picture has begun to be observed. Now, moving on to our measurements of RAA. So this is a measurement using the pi0. We do see a deviation from unity. It's on the 4 sigma level. And when you start to compare just the shape of this, or what we measure in oxygen compared to what we've measured in lead and xenon, you see similarities in the shape, in the sense that this thing drops a little bit higher PT and begins to rise again. And that's something you see in lead on xenon. And the shape is a complete contrast to what you see in proton lead. So this starts off low and then goes high and then pretty much saturates at 1. We've, of course, compared to sort of 2 scenarios. One is a PQCD baseline scenario. So this is just introducing cold nuclear matter effects, e.g. the modification of the nuclear PDF compared to proton. And this is denoted by the blue curve. And then you also see a calculation from Will Horowitz and his student Coleman. I think Miklos is here anymore, but Will Horowitz was Miklos' student. And at least when you compare the data, it arguably favors the energy loss scenario rather than just the cold nuclear matter scenario. But certainly what we need to do experimentally is reduce the size of this normalization uncertainty. A lot of this, I mean, there's various sources to this, but one of it is estimating the trigger inefficiency. Because we're measuring rates, we need to know the number of collisions that actually happened, and that you need the trigger inefficiency. And there's also some uncertainties that come from the number of binary collisions. But we're working on doing that. These uncertainties affect both the PP collisions and the oxygen collisions, and there's various strategies to see if we can get this down, and we expect to be able to do so. Just comparing our REA for the pi zeros with CMS, we see very similar values, certainly consistent within errors, which I think is great to see. CMS went a bit of the extra mile in terms of comparing various model calculations. Don't ask me to tell you what the ingredients are in all of them, but it's still a useful comparison to make. And Atlas actually did something quite interesting, and it measured these dijet asymmetries. So you just take a dijet, you have the PT of 1, and you divide it by the other, and there's a corresponding distribution of that. So these are the measurements in proton-proton collisions, and then peripheral oxygen-oxygen, and then central oxygen-oxygen. And there seems really some indications of a change in these dijet asymmetry distributions, which we've certainly seen for lead-lead collisions. They do look much more different compared to PP. So just some final slides, just to say there's certainly much more to come from Alice. We will certainly leverage our full potential to investigate different aspects of QGP behavior. What we have here is a projection for our strangeness, strange over non-strange yields to sort of fill in this gap a little better between proton lead and lead. I think heavy flavor production will be very, very interesting because heavy flavor, the energy loss tends to be predicted to usually be a little less compared to the light flavor, which is what we're sensitive to with the previous measurements. And I think it would be, of course, to be very important to determine that. And then finally, ultra-peripheral collisions, which I think will be rather critical to constrain these cold nuclear matter effects a little better. What I will say is for these nuclear PDFs in oxygen, there's no data. So this is extrapolated from different nuclear PDFs from sort of neighboring nuclei, so to speak. So it'd be very good, I think, with UPC collisions if we can put greater constraints on that. I'll finish. I'll just try and keep it simple. I say that the initial LS results indicate OO and neon look like a QGP. Whether they swim and quack like one is something that we'll really have to see. And it's also good to see a common picture as a measure across all LHC experiments. And I'll just finish with a joyous summer party that we had 1 week after. Quite a bit of fun. I was there, John was there, and many of our other Alice colleagues, and we have a drone shot of everybody there. So, thank you.
This was very nice, Anne. Thank you very much. So let me see if there are questions. I can start with one. Can you go back to your slide 20? I just realized something. And this will be doing physics with crayons. So, I don't know what so I see two lines here, which is this one. Sorry, goes along all centralities, and I see something here. While hydro tends to do some continuous evolution with centrality. Was there any discussion of this? This is quite striking. I mean, it looks like the deviation from that flat line is only in 2.5% central collisions.
Yes. So the stronger the deformation is in neon, the earlier it will start to kick in. But you're right, it does. So I think it can either indicate that we have perhaps a smaller one. I think the trajectory people did follow it up with changing these sort of subnucleon widths. So I think what you do in the end there is you're sort of adding more fluctuations, which is dampening the effect of the shape. Yes, I mean, I would agree with the comment is the behavior is a little different. And as for the reason why, yes, we'll have to think about it a little.
Well, kudos to the PGCM because they stop exactly where things start getting interesting.
Well, it's the hydro implementation that does, not the nuclear model that can run at any centrality.
Okay. So it's really all in the shape. So okay, there's a question online.
Hello.
Hi.
Yes.
Hi.
Can you hear me?
Yeah.
Hello.
Yeah. Thank you for the nice talk. Can you say how exactly is this subnucleon width defined? I mean, the picture doesn't really say. I mean, why do you use that the lower left corner instead of the upper right corner, for example?
Yeah. So this width is you have a constituent quark, and that has a Gaussian distribution, and the subnucleon width is the width of that Gaussian.
So that size is much smaller than the size of the nucleon. So
Yes. And in this case, it's 0.1 Fermi, and of course the nucleon is 1.
Okay. Thank you.
I think Miklos wanted to say something.
Miklos?
Yeah, hi. Can you hear me?
Yes.
Very nice talk. New data, beautiful. Could I see slide 24, which compares all the theory models? Is this published somewhere that I'd love to be able to look at the differences here? Horowitz, Williams' calculation, I don't know which one is that, but his emphasis is that the corrections to the theory that are neither Q hat nor just the simple energy loss perturbative ones, is that the higher order effects are important. That's at least what he tells me. And that's the latest preprint that he has, some giant 100-page paper. And so I just wanted to look at it in a little more detail. Where is this published, by the way? Because I want to be able to see it, not on a tiny screen.
Miklos, just go to the initial stages conference, and the talk is by Austin Batty on Thursday, and there I think he has all the references for the models.
We can get a link for you, Miklos.
Okay, so if somebody could email me at the usual places. So this kind of offers a ground for looking at the differences between the various approximations that have been around for about 20 years or so. And this has a tremendous amount of information that will take a while to sort. There's a rather large, in the sense of, going from one theoretical approximation to the other. And it's actually quite surprising to me that oxygen, of all things, can act with such precision, super high data precision, can offer a grounds to reveal a little better which approximations are better or worse. So congratulations. I mean, I can't believe that the data is so beautiful. It's just spectacular, and it offers a way of moving on from the old ideas to like Horowitz, which looks at corrections to the corrections in a very novel way. Okay, thanks.
Thank you, Miklos. I mean, what can I say? Heavy ion collisions are still fulfilling their discovery potential, and it's good to see that we can be surprised, but also we can be quite accurate with many of these measurements.
Well, it's also ridiculous that it was done in a week. So John and everybody at the LHC, machine, this was tour de force. Were
unbelievable.
Yeah, it's not so much me anymore, Roderick and company.
Well, you build a foundation for this to happen. Okay, take some credit, John, please.
Okay, sure. Right.
We have Spencer, and then Feng.
So very quick. So do you have any plan to have proton oxygen?
We've measured the multiplicity. I just don't have it in my my slides, but they were shown at initial stages. So we measured the proton oxygen multiplicity distributions.
I mean proton oxygen collision.
Proton oxygen collision.
Yes. This is the DNDY.
Yes.
But I think, Ant, if I can interject, so you're the upcoming management board, and I'm outgoing management board. I think these data tell us we should measure it.
Yeah.
Okay.
I mean, you're talking about cold-nuclear effects.
So if possible, we should certainly do more.
All I can say is with the pi zero, we are working on trying to measure the RP oxygen. It's a little more tricky because we don't have the same PP energy. So one has to do an extrapolation between the top energy at the LHC and then the reference energy for the heavy ion program. But it certainly should be possible. And when we publish this paper, we absolutely have to put proton oxygen points if we can. But that's the plan.
Spencer?
Yep. So very nice talk. I had a question about one of your transmutation plots. I was going back, the one with showing the change on neon with time. Yeah, so this one, if you look at the plot on the right, the second and third points are above the first point for the neon. That indicates that the average multiplicity, I guess, is rising. If you take that seriously, it looks statistically significant. I'm not sure if it is systematically, but that would indicate maybe that there's some contamination in the beam early on that burns off, or what?
Yeah. Well, it's interesting because we also discussed potential oxygen that was, so the oxygen, John knows more than me, but the neon and oxygen are separated. Oxygen goes in, but the neon has potentially a little bit of oxygen left. But then if the oxygen was in the neon beam, because it has a smaller cross section, it's not going to burn off as quickly as the neon. And I'd have to think about what that would mean for the for these mean multiplicities, Spencer. But we're gonna, yes, there's no systematics on this. It's a performance plot, but at the moment we're changing a bunch of event selections, and perhaps we'll make it into preliminary at some point and put some serious errors on it.
Okay, thanks.
Yeah, if I can interject there, it's just the residual contamination of the beam could have been about 0.5% oxygen in the neon beam from the beginning of the fill, or it could be zero. The measurements taken near the source are have an error bar, and it's like that, between 0.5% plus or minus 0.5%, more or less.
Okay.
Okay, I just want to say, Ant, if you go back to the RAA plot and what Miklos was commenting on the slide, there is uncertainty at 1 for both CMS and Alice. So we're still working on our uncertainties. I don't know if CMS can do more, but we've done a pretty good job, I want to say. I mean, we bang on the data with CMS, despite the fact we still have to recalculate our overall normalization of the curve.
Yeah, I suspect we've been a bit too conservative, because if this was the real error,
Well, now we can say it. Now we can say it. But okay.
If that was the real error, then that would be the expected difference between CMS and Alice, and it's much smaller. So this gives us, some indication that we've perhaps been a little too careful. But when we publish, we'll be even more careful to evaluate that, and I expect it will be smaller.
And by any chance, do you know, is there any of that coming into the theory curves right in the middle? Is there any of that width related to the Lauber scaling, or this is really theory uncertainties? I'm really asking about theory uncertainties. I mean, if data is so precise, you could, ask why theory cannot get more precise, but probably Miklos has a word on that. And then we still have a question from Peter. So, what do you know about theory curves?
I know Miklos can answer that better than me. I don't know the origin of the theory.
Let me point out Zakharov's thing in the billion different curves here on the middle, which is the one that goes right through all the data.
Yeah.
This really surprises me because long ago, about 20 years ago, when I was working on this stuff, this monopole, the little m is a magnetic monopole, which goes back very, very far in QCD, arguing what are the roles of magnetic monopoles in a quark gluon plasma. And this was something we also investigated with Zakharov. It seems to indicate that there's great sensitivity versus Q hat. For example, the simple Q hat type of approximations, the BDMS green and the orange lie significantly above. And right in the middle is this monopole, which is maybe giving a lot of hints about the fact that it's not just quarks and gluons. Confinement can be described with a fraction of color magnetic monopoles in the transition region. This is would be very nice, and what is shocking is that the data is so damn good. It starts to be able to differentiate infinitely broad approximations that can be ruled out finally in one way or the other. So there's a hell of a lot in this middle. I don't know what is beeping here. Anyway, my time is up, so that's it.
Thanks, Miklos. So last question, I suppose, Peter.
Yeah, sorry to be the fly in the ointment here, but I would caution about interpreting any of these REA data in terms of jet quenching. Not shown here, but was revealed at initial stages and has been explored, further afterwards. As Ann indicated, there are really no direct data on gluon shadowing in oxygen. It turns out that EPPS 21 has quite substantial effects, even approaching, well, yeah, so there's this, and also compared to CMS, even approaching the level of suppression that we see, especially taking into account the normalization. And Mateusz, this is not related to the precision of the data. The precision of the data are what they are. The uncertainties in nuclear shadowing and initial state effects, it's pretty hard to see how to overcome them before there's some more input into shadowing, probably from the EIC or maybe LOX direct photon measurements in oxygen, something like that. So I think this is still very much open. And let me
Right, but
point
Peter,
out
this is related to what I asked, right? What
Yeah.
determines the T curves uncertainties?
Right.
And
So I
if
think the
shadowing is
shadowing
not-
issues. Let me
Right.
also point out that this is all for minimum bias oxygen, which is fine, but inevitably, and especially in comparison to the systematic flow measurements, you want to do event activity correlated measurements, and there you're completely at sea as how to scale these things. So the bottom line is that inclusive measurements, and I think this has been shown before in these small systems, inclusive measurements are really quite limited due to their large systematics, and one has to go to other channels, in particular coincidence channels, to really do precision jet measurements. And this is in progress, and in progress rapidly, but that's a different talk.
Very good, Peter. A good grain of salt. So, but this is exciting times nonetheless. Ant, I would like to thank you very much for your talk. Thank you for staying up late. Thank you, John, everybody. Hello, Houston. Thank you so much for joining us. Maybe not the last time. And yeah, let's give a hand to Ant.